In this video, we'll be focusing on the following concepts: logical truth, logical possibility, logical necessity, and tautology. So let's take a look at them. Alright, so a logical truth is a logically necessary proposition, and we're going to unpack the concept of logical necessity here in a little bit. But just to think of some examples, A is identical to A, for instance. So if we remember, in FOL, our names are individual constants. So for any instance of a name, it can only pick out one object. It's not like the English name Bob that several people can have. Only one object can have the name A. So these two names have to be picking out the very same thing, whatever that thing is. And of course, a thing has to be itself. You have to be identical to yourself. You have to have all of the same properties that you have. So by the meaning of numerical identity and the fact that these names are individual constants, there's no way for such a proposition to be false in FOL. It is a logical truth. Here, if I say this reads as if then, so if P then P, and the idea is if P is true, if you get to accept P is true, then P is true. If it's true, then it's true. So there's no way for this to be false, and it doesn't matter what information is contained in P, whatever proposition it is, whatever statements, whether it's grass is green, the snow is white, so on and so forth. Here we have what's called the law of excluded middle, and since it's a disjunction, it's just saying either P is true or it's false, right? Because that's negation P. And so it doesn't matter what statement it is. A statement about a world is either correct or it's incorrect. It either gets how the world is or it doesn't get how the world is. So this is, again, always true. And the fact that they're always true as a function of the logical connectives or the function of the meaning of the words, that is why it's a logical truth or why it's logically necessary. All right, so let's talk about logical possibility. If a circumstance, situation, state of affairs does not entail a contradiction from the mere rules of logic or the meaning of the words, then it's logically possible. So just to give you a sense about how something can entail a contradiction just by the meaning of the words, think of a proposition that says some bachelors are married. So this is self-contradictory because the very meaning of bachelor is to be unmarried. So it's impossible then, it must be false. It always has to be false to say that some bachelors are married, since it's saying of something that is unmarried that it's married. So that would be one example. Or we can consider a different one, where we just rely on some of the rules of logic. If I say P and not P, just thinking about this, we know that what I'm saying is this is true and the very same proposition is false because we have the negation out in front of it. So we're saying that a proposition is both true and it's false. But that can't be the case. Either what you're saying about how things are is correct or it's incorrect. It can't be both correct and incorrect. So just by the meaning of conjunction and negation, we know that that it entails a contradiction, that it's self-contradictory, cannot be true. Okay, so logical possibility is broader than physical possibility. And what I mean by that is there will be things that are logically possible but are physically impossible. For instance, take the case of accelerating past the speed of light. That turns out to be physically impossible. But the reason that that's impossible just has something to do about the constraints of the world in which we find the physical world in which we find ourselves. It's not a matter, the reason why it's impossible for us to accelerate past the speed of light isn't a matter of the rules of logic, and it's not a matter of the meanings of the words. That's something that scientists had to go out and discover, doing various tests or what other sort of considerations that physicists need to engage in. It didn't just take a matter of conceptual analysis, like in the case of Bachelor, to see that it's impossible for bachelors to be married. So it's logically possible for us to accelerate past the speed of light, since the rules of logic and the meaning of the words don't prohibit that, don't get us into a contradiction. Nevertheless, there's something about our physical world that makes that impossible. Whereas, of course, it's physically possible in our world to move around or, engage in all sorts of other behaviors. All right, and then Tarski's world. So logical possibility is also broader than Tarski's world possibility, and that's because something is Tarski world possibility is Tarski world possible if and only if it is a circumstance that can be built in Tarski's world. So, for instance, here's something that's Tarski world possibility, that something is a cube, right? A, B, C, whatever that object is. That is a possibility in Tarski's world. And clearly it's a physical possibility as well. It's also a physical possibility for something to be a sphere. But that's actually Tarski world impossible. In Tarski's world, there's no option for any of the objects to be spheres. The only options that we have available is cubes, tetrahedra, and dodecahedra. So it's Tarski world impossible for A, B, C, D, whatever to be a sphere. But clearly, it's logically possible. There's nothing about the meaning of sphere that makes it impossible for something to be a sphere. So it's not logically impossible for something to be a sphere. It would be logically possible, but in Tarski's world, it's impossible. All right, so let's talk about logical necessity, tautology, and their relationship to one another. So a statement that's logically necessary is one that must be true. It's when a circumstance must be true merely as a result of the rules of logic or the meaning of the words. We've already seen a couple of examples. One was if P, then P. So, for instance, if the grass is green, then the grass is green. Of course, that's a true statement. If it's true that the grass is green, then it's got to be true that the grass is green. Or a different statement, if A is to the left of B, then B is to the right of A. So this is true partly because of what the logical connective here means, but also the meaning of left and right of, and the fact that they're inverses of one another. So those are logical necessities. Those are logical truths. tautologies are a subset of logical truths. They're a subset of logical necessities. So some things will turn out to be logical necessities that aren't tautologies, but all tautologies will be logical necessities. So we can determine whether something is a tautology by appealing to our concept of a truth table. Our truth tables are only sensitive to the meaning of the logical connectives. They're not actually sensitive to the meaning of the propositions that are being stated in the various different predicates. So for instance, it wouldn't be, a truth table isn't sensitive to the meaning of left of and the meaning of right of. It would ignore those. What it wouldn't ignore is the conditional sign, the disjunction sign, and the negation sign. Okay, so one of the things that we can use truth tables to see then, to look for, is to see if the meaning of the truth functional connectives that are available to us make it such that a proposition has to be true. That is, when our reference column exhausts all of the possible truth combinations. In this case, since we only have one proposition, there's only two possible truth combinations. The situation in which P is true and the situation in which P is false. And we see that no matter whether P is true or P is false, our sentence P, or not the case P, is got to be true. So for any truth combinations that are out there that are available to us, that sentence must be true. So in virtue of the truth functional connectives, P or not P has to be true. It won't matter. Again, it's not going to matter what the content of P is. It'll still have to be true anyway. And so really then what we can see is that for a tautology, what makes something be a tautology as opposed to some other type of logical necessity is that what is forcing the proposition to always be true is the truth functional connectives. When that's a case, you have a tautology. When you're relying on things that go beyond the truth functional connectives, that forces something to be true always by the meaning of the words and the rules of logic, then it's still a logical necessity, but it won't count as a tautology. All right, so tautologies are a subset of logical necessities, logical truths, and we can use truth tables to determine that, and a truth table will show that something's a tautology if the column of the main connective of the sentence we're doing the truth table on is nothing but T's. So if those were all T's, then this would be a tautology. Of course, they're not all T's, so it's not a tautology. In contrast, a sentence is truth table possible when in at least one of the rows representing our various circumstances, we get at least one T. So here we get at least one T, so this sentence is truth table possible. That is, as far as the truth table is concerned, remember, it ignores the meaning of whatever the sentences are that are in P and whatever they are in Q. It's only sensitive to the various truth functional logical connectives that are available to us. As long as there is a situation in which being only sensitive to the truth functional connectives, it says that it could be true, that there's one situation in which it's true, then it's truth table possible. So our one circumstance in this case is the situation in which P is false and Q is false, because that's going to make this sentence true. And why call a truth table possible? Well, here's all of our possibilities as far as our truth table is concerned. And there is a situation in which our sentence turns out to be true in our possibilities. Again, namely this one. All right, so notice then that all tautologies are truth table possible because all tautologies will have at least one of its rows be T for the sentence in question, because the whole column of the truth conditions for a tautology are true. So tautologies are always truth table possible. We can also contrast truth table possible with sentences that are truth table impossible or truth table contradictory. So take, for instance, this truth table. And this sentence. Since we only have one proposition to worry about in our reference column, there's only two possibilities, two possible situations. Namely where P is true and where P is false. So we can go ahead and just replicate that pattern here since this is P. We know that for not the case P, we've got to flip the truth value around. So since this is T, we need an F. And since this is an F, we need a T. And the semantics of a conjunction is that a conjunction is true if and only if all of its conjuncts are true. It's false otherwise. So in this case, we have one of our conjuncts true, but one of them's false. And since one of the conjuncts is false, we know that it's false there. And again, one of our conjuncts is false. So even though the other one is true, we know that this is going to get the value false. And now we have no row for any of our possibilities. We have no row in which there is a T. They're all F's. So that tells us that this sentence isn't truth table possible. It's truth table impossible or truth table contradictory. Alright, so I just want to end this video by talking about some of the way that these necessities that we've discussed relate with one another. So tautology is a logical necessity. We said it's just a special subset of logical necessities. Namely, tautologies are logical necessities that are only sensitive to truth functional connectives. Okay, so all of our tautologies are going to be logical necessities. By the very meaning of the logical connectives, they have to be true. Logical necessities include tautologies, but also include the meaning of other logical operators and the meaning of the words. So just as one example, if P then P is a tautology, It's got to be true whatever is contained in P. And so it also has to be a logical necessity. And as a result, then it's also got to be a Tarski's world necessity. A is identical to A. Is a logical necessity, but it's not a tautology. It's not a tautology because this is a predicate, not a logical connective. You might confuse it with a logical connective, but it's not. It's a predicate. It's the identity predicate. So just by the meaning of the identity predicate, we know that A has to be numerically identical to A. And again, that means it's got to be necessary in Tarski's world. In Tarski's world, one of the things that is necessary is that something has to be a cube, a tet, or a dodec. But of course, that's not logically necessary. There's all sorts of other shapes besides cubes, tetrahedra, and dodecahedra that an object can take. But those are the only ones that can be taken in Tarski's world. And so an object is gonna have to be either one. It's got to be one of those, right? Either a cube, either a tetrahedron, or either a dodecahedron. All right, so if something's a tautology, it's got to be a logical necessity, and if something's a logical necessity, it's going to be a Tarski's world necessity. But it doesn't go back the other way. Just because something is a Tarski's world necessity doesn't mean it's a logical necessity, and just because something's a logical necessity doesn't mean that it's a tautology. All right, and that concludes this video on logical truth, logical possibility, logical necessity, and tautology. Thanks for watching.